Hello, hello everyone, and welcome. I'm Murthy from the Azim Premji University and part of the editorial committee of iwonder. iwonder, and I'm sure you also, iwonder is a science magazine for middle and high school teachers. It features writings about science, about the many dimensions of science, the teaching and learning of science in class as well as outside. This magazine is published by the university in English, Hindi, and Kannada twice a year. If you are a practicing science teacher, we invite you to write for us. Please send your idea in about 100 words to iwonder at apu.edu.in. All the information is below in the description. If you'd like to receive updates of each webinar and a free print version of each issue, subscribe. You can also follow us on Facebook. So welcome back to our monthly webinars. As you know, the second Wednesday of every month, we invite authors of an article from iwonder for a live discussion. And for this webinar, we have here with us Rajaram Nityananda, author of the article Seeing the Invisible, Imaging a Black Hole from our August 2019 issue. Rajaram Nityananda recently retired after teaching at the Azim Premji University for about 7 years. Prior to this, he was at NCRA Pune and earlier at Raman Research Institute in Bangalore. He's been the chief editor of Resonance and the Journal of Science Education. Much of his research work has been theoretical in areas of physics concerning optics and astronomy. Rajaram, thank you and welcome. Before we start, let me explain how we are going about with this discussion. We will have questions about the article. We'll discuss questions about the article with Rajaram for about half an hour. And after that, we would discuss questions from the audience. And all of you out there, we welcome your questions. And please put your questions in the chat box for discussion. So, Rajaram, let's start with the obvious. Very briefly, what is a black hole?
Okay. I think the term black hole has entered the popular imagination. But as originally proposed, it was a purely theoretical concept. No one had seen one. And the idea was that if the gravity of an object was sufficiently strong, even light could not escape from the surface of that object. Now, what do we mean by strong? Number one, a very large mass, like that of a star or bigger. And number two, a very small radius, because we all know that gravity becomes stronger and stronger as you come closer and closer. Okay. So that's the very brief description of a black hole, but I'm sure we'll get more into it as we go into this webinar.
Yeah, but how do astronomers determine where to look for a black hole out in the sky? And they must be far.
Okay, this is a very long story. All right. As I mentioned, black hole was something in the minds of some physicists, like Einstein, for example. It was in his work that the proper mathematics describing how light will travel near such a body, how it might escape or not escape, was worked out. But this was all pen and paper, okay? We're talking of early 20th century. And astronomers basically found a huge gap. To make the sun into a black hole, you would have to compress it to a radius of 3 kilometers from, 700,000 kilometers. So such a huge gap that they ignored it. But then gradually astronomers realized that the sun also, towards the end of its life, can shrink. And, various things can happen. So gradually, by the middle of the 20th century, people started taking very, very compact stars seriously. Okay? But how do we see them? Especially if light doesn't escape, right? So there the matter rested. And then when people started seeing very energetic X-rays or ultraviolet light from the centers of galaxies, they tried every possible explanation for where this energy comes from. And very surprisingly, the best explanation turned out to be that there is a black hole sitting there, that matter is falling on it. And of course, once it enters the black hole, it's not going to give you any light. But on its downward journey, it picks up tremendous speed, gets very hot. And so paradoxically, astronomers look for black holes in locations where enormous energy was pouring out in the form of radio waves or X-rays or ultraviolet light.
Is that how they chose or zeroed in on M87? Is that the number?
Yes, but there's little more to it because there are many, many galaxies who show some activity at their centers. So this was a long process of weeding out. Okay. And basically, one ultimately needs to pictures. And the initial pictures, in fact, right up to this recent work, were not detailed enough to show you the black hole. Okay. So people kept making it better and better pictures, and it turned out that M87 was a good candidate for two reasons. One is the black hole in it was considered to be extremely massive, right? And that's indirect evidence from the stars moving around the black hole. But also, the distance was not too far away, because even if you have a large object, if it's too far away, it's very hard to make a picture of it.
Yeah, and so as you also mentioned, if nothing can escape a black hole, how does one go about obtaining an image? And is this not a photograph in the sense of a photograph?
Okay, I'll take the question in two parts. One is, how do we get around this problem that the light cannot escape from the surface of the black hole? Let me elaborate on what I mentioned earlier, that the matter falls in and picks up a lot of speed and becomes very hot. Now, actually, if it was aimed directly at the black hole, it would fall in very quickly and it wouldn't have enough time to give you a lot of energy. However, typically, a matter falling from far away will miss the black hole and it will orbit around it. So in the process of orbiting, it goes round and round, and there's some friction. So we all know from even the recent Chinese satellite, which crashed, in that when an object orbits and there's some friction, it keeps coming closer and closer. So this is the basic scenario, that there's this gas around the black hole, it's orbiting, the friction generates heat, and the gas is gradually sucked into the black hole. But in that process, is able to give you all this energy. So that's the first part. The second part is the image. Now, the main challenge here is that I told you black holes are very compact. So this ring of very hot matter is also going to be pretty small, maybe 3 or 4 times the size of the black hole, but still very, very small. So you need the technology to make images. And I have to confess that the one I talked about in the article is not an image in the sense of a photograph. It's made very indirectly receiving radio waves, which I can elaborate on if it's of interest.
Yeah. Is this coming from a telescope? You mentioned EHT. So how does it work, and what are the technological challenges in such an imaging procedure?
Okay, I thought it might be nice to actually show a picture of this image that we've been talking about, and also a picture of a small part of the telescope. So let me try that. Right. Yes. So this is the picture which was splashed on the covers of magazines and newspapers and so on a couple of years ago. I'm sure many of our viewers might have also seen it. So you see this matter, which we believe is orbiting the black hole. And actually, if you ask, where is the black hole in this picture? The answer is, it is this region. And normally we would have seen radiation coming from this region, but it has been swallowed up by the black hole. Okay. So in brief, this is the image. The amazing thing about this image is how small it is in angle. So I think we are all familiar with the size of the moon, right, in the sky. So you have to go to 1 billion times smaller. So, you can imagine what kind of telescope you need for that. Now, let me say a bit about the telescope itself. So here I hope Is this clear? Right.
Yeah.
See the beautiful clear skies and desert. This is in Chile, in South America. And astronomers go to these very high altitudes, this is 5,000 meters or more, and put these telescopes there so that these very short radio waves with a wavelength of a few millimeters can be received. Now, this is a very powerful telescope. It was not built to image black holes. Okay, several such telescopes were there all over the world. And then people got the idea that we can combine the signals from all these telescopes and imitate a telescope which is almost as big as the Earth. Okay, so that in brief is this collaboration. It's called Event Horizon telescope. So telescope is not one telescope. It's this one plus one in the South Pole, one in Hawaii, one in Spain, one in Mexico, one in US, one in Greenland, so on and so forth. Okay, and this combination gives you the image which you saw. And Event Horizon, I should explain, is just a technical name for the surface from which light cannot escape. Okay. So, yeah, so I hope these two pictures contribute
Fascinating.
to
Towards,
giving.
yeah. Towards the end of your article, you write, even more fascinating, but still unsolved is the problem of what happens to matter once it crosses the event horizon. What role does technology, and particularly computation or computing power, play in the study of astrophysics?
Okay, so that's a broader question. So the computing power has two roles here. I mentioned that these signals from different telescopes have to be combined. Now, from the geography, it's very clear that you can't combine them in real time. If you're in the South Pole, so these signals are recorded, enormous volumes of data. I mean, we're used to, megabits, gigabits, terabits, but this goes to the next level, thousands of terabytes, what is called petabits. These are recorded and they are played back in a central computer and they are combined. If you think about it, even an ordinary telescope combines the light falling on different parts of the mirror and brings it to a focus. So all this is now happening in software. So that is, in brief, the role of computer technology in making this picture. But then there is a role of computer technology in modeling this picture. Now, I gave you a very simple-minded description saying the gas goes on in orbits, there is some friction. But suppose you wanted to make it very quantitative. Then, beyond a point, pencil and paper doesn't work. So you have to, make a very elaborate computer program which will account for each parcel of gas, how it is heated, what radiation it gives off, how it shrinks and moves towards the black hole. So that is the part which has already happened. Now, in the end of the article, I talked about something which has not yet happened, but which people are trying. And that is of somewhat theoretical interest, because as I told you, once something goes into the black hole, from outside you don't see it. But physicists are curious people. So long as there is some physical laws governing this, you would like to know what happens. And that again turns out to be a very difficult problem, which is now being put on the best computers.
Yeah. Could we say light, even though it is light, but still can't escape the black hole?
Yeah. Yes, I think that's so. Light has gravity.
Yeah.
You want to put it that way, right? We talk of levity and gravity. So,
right. So another possibly related question is a point you make in the article regarding the conditions in which people study, lab physicists versus the astrophysicists, and the amount of control. Astrophysical systems do not offer control.
yes. I mean, although we use the word astrophysics, one may well ask, why is it so different from laboratory physics? And the answer is precisely what you mentioned, Murthy, that we have to accept whatever we receive from the sky in astrophysics. Of course, of late, people have sent spacecraft to the solar system. So gradually, solar system is going away from astrophysics and coming into ordinary physics. So if you have something sitting on Mars, drilling a hole, taking a sample, well, that's geology. But beyond a certain distance, we have to rely on this kind of remote sensing. Okay. Therefore, the style of astrophysics is a little different. people come up with lots of models, and typically many models would initially explain the unlimited information you have. But then people will say, okay, this model predicts that you will get more X-rays. That model predicts you should have a magnetic field. Let's go and look for it. So there's a good back and forth between observation, which is using these telescopes, and not just the radio telescopes you saw, but every other kind, X-ray, visible light. Many of these telescopes are located in our country. I could say more about it at some point. So that's one part. And the other part is that once these observations are in, the theorists go back to the drawing board and then say, okay, we have to remove this theory, we have to modify that theory. So there's a lot of interesting things happening. The theoretical work is done by small teams, but the observational work of this EHT kind, that paper had 347 authors. So it requires tremendous coordination, planning over 10 years, and so on.
So if you could come back to the many middle and high school teachers in our audience today, what are the three concepts today and later? What are the three concepts in science that you hope to highlight for them from this article?
Okay, the article itself was somewhat brief, but I can expand on it now that I have a chance to interact with this group. First of all, gravity is something which enters very early into the curriculum, and people think of it in terms of a stone falling. But the fact that it can be a source of energy is a point which can be made with everyday examples, right? Coconut falls and you would like to avoid it falling on your head. On the other hand, when water falls down a huge waterfall, the energy can be harnessed to generate power. So I think these are connections which can be made. So that one is gravity. The second, which is also introduced early, is the concept of a telescope, which can gather light over the area of a lens or even a radio antenna and then focus it. So, and the third, of course, is and I think that's the most profound, and which is Einstein's insight, though people had guessed at it earlier, that although light travels at such a tremendous speed, it is not immune to the force of gravity. But in the laboratory, we don't see it. If you shine a laser beam, it seems to go in a straight line. But on a grand cosmic scale, when a ray of light passes, a galaxy or the sun or a black hole, it gets bent. So I would say that one could make these points. I don't know about the classroom. I think our teachers already have very heavy syllabus to handle, but I think there are more relaxed, informal settings where, to a group of interested students, whatever has happened in the classroom can be elaborated in this way.
Yeah. So I keep wondering about how simple concepts from school can be made to extend into complex things. So, for instance, is what you're talking about as simple as, let's say, I take this piece of eraser I have here and I throw it with some velocity, it goes a little bit up. If I throw it a little bit more, it goes even higher. And if I throw it with even larger, it escapes Earth. So does light also work like that? Is that does it lead to a general theory of relativity, which is very complex?
Actually, one of the very paradoxical things about general theory of relativity is that light is kind of frozen. Now, this has to do with the fact that so as far as an observer far away is concerned, the light never comes out. It doesn't even move. But if you were there, at that point, you would see the light going outward, but that is a consequence of your falling inward. Okay. So I'm sorry, this sounds a little abstruse, but so I think I would say the analogy that I sometimes give is imagine that there is this escalator, it's a kind of staircase. So the staircase is moving downwards and you are trying to run upwards. So with respect to the staircase, you are running very fast, but you're not really able to move away from the floor. Okay. So, but I think this may not be completely appropriate. Maybe, if students in the 12th standard read Stephen Hawking's book on black holes and they ask, how is it light doesn't escape? I would give them this analogy. But even at an earlier class, the idea of escape velocity, which you gave, I think it should be illustrated In fact, India has a very powerful space program. So the idea that, and we have sent things to Chandrayaan, Mangalyaan, and so on, which have escaped the gravity of the Earth. So the idea of escape velocity is something that is not remote to them anymore, right? ISRO has beautiful videos on its website showing you the liftoff from Sriharikota. So I think these concepts can be made very real for the students. The idea of escape velocity. And of course, it's a very high velocity.
And as you've shared in the article, imaging a black hole is also a highly technologically intensive, cutting edge kind of research development as well. So as teachers, we often find there is this tension in introducing developments in cutting edge research versus fundamentals. Where or what is the balance in all this?
I would definitely say that in the earlier classes, one should not try to make too much of this distinction. Okay. And I think it's possible to make a seamless connection between the devices that we use in everyday life. Nowadays people have mobile phones which have cameras and so on, right? And they receive radio waves. So I think science and technology should certainly be connected. And we never know which area students would excel. And I think that's true even when they come to our undergraduate program. As you well know, we see them coming in with certain ideas. We try to expose them to experiment, to theory, to computation, to pure ideas like gravity, or even to applications, right, in the lab. And then finally, they are able to choose. And perhaps the real choice occurs even later after your undergrad. Mm-hmm. So I would say one should emphasize connections and breadth rather than make a distinction at this point.
So in your article, you share the entire story of the journey of research into black holes from the conception of an idea, a theoretical possibility, to an image that we see, observational image. Do you think this has the potential to offer students introduction to how scientific processes and how scientists work, basically? And if yes, which aspects of this journey would you like to highlight for students at school level?
Okay, so this particular journey, I think I would like to highlight, of course, the role of technology I've already mentioned, and the whole subject of astronomy with radio waves depends on technology. I think I should mention that these very short radio waves of few millimeters have recently come into technology, but they were first made in the lab in Calcutta University by Jagdish Chandra Bose in the late 19th century. And this is an achievement that we don't tell our students about. Okay, so that's just a side remark. So apart from technology, there is collaboration and completely international collaboration. So that's one aspect. However, I think going a little beyond this article, one can do case studies of different kinds. Okay, so let me take something from biology, where there is this beautiful molecule which is in every cell of ours called ribosome, which actually manufactures proteins and so on. So its structure was recently determined, and that was a different kind of collaboration, slightly smaller, but still different groups in Israel, Cambridge University. And the person who won the Nobel Prize from Cambridge University actually did his master's in Baroda. So I think we shouldn't emphasize just one style of science. This is somewhat big science. It's not the biggest science, by the way. This has only 347 authors. Many of the particle physics papers have 4,000 authors, because the machines are even more complex. They may take 30 years to build, and so on and so forth. So I think we should give students exposure to. And there are also examples of very nice discoveries made by two people in a lab. So I think I would again, not foreground any one model of science, because we again don't know which model the students may go into. And I'm not making a distinction between science and technology here.
Yeah. So the idea of this black hole and seeing this image can be really awe-inspiring and wondrous to the student on the one hand, and very challenging to comprehend, as we've discussed. So what are your thoughts on how teachers could address this to keep the spirit of wonder alive, as well as satisfy the curiosity in the young students' minds?
I think there's no simple answer, and I can't speak for school students. But after all, we get students who are just 1 year out of school, and they are again full of enthusiasm based on what they have read. And I find that you have to take a different approach. Some people would actually like to know more and more details. Now, there's no point in giving them a fat textbook. I think one must be realistic and say, okay, to understand this black hole, these are the theories, this is the kind of mathematics you need, and this is where you need to start. Okay. But to others, perhaps one can give popularized explanations, and there are some lovely articles of that kind. In fact, some of the nicest articles are written by the founder of the Bangalore Planetarium, Professor C.V. Visweshwara. They are available on the website, specifically on black holes. Here's a lovely article on black holes for bedtime, and it has cartoons which he drew himself. So I think we have to find the right material, and thank God we now have the internet, and I'm sure we can help teachers connect to a range of materials appropriate for a range of students.
And I'm sure we'd also get some ideas about the experiences and the teachers' own ideas over here with us at this webinar. So could we take questions from the audience?
Yes, I'm looking forward to that.
Yeah. Archana Dwivedi writes, I read that black holes keep expanding, and I assume that there would be many black holes. So could it ever happen that these black holes engulf other stars or part of galaxy?
Yes. So I should say something about the size of a black hole. It's proportional to the mass, strictly proportional. So if you have something, the mass of the sun, its radius would be 3 kilometers. If it is 100 times the mass of the sun, it will be exactly 300 kilometers. So in some sense, a black hole is a very simple object. It's described by these equations of Einstein. But one of the complications which you have with stars are there because it's really pure gravity. So that's one part. Now, in terms of engulfing other black holes and so on, there is something which I don't know if it has been covered in iwonder, but people have observed two black holes going around each other and ultimately merging and becoming one. And even the process I mentioned of gas going around a black hole, you could say it's a black hole engulfing a cloud of gas. And there are also examples, live astronomical examples of stars falling into black holes. Then you don't get energy in a continuous fashion. You get it in a burst. So actually, Archana's question has an answer in very contemporary astronomy. Except I should make one caution. It's a very small object, heavy object, but small, sitting in the center of the galaxy. Now, most objects will orbit around it. And unless you remove the energy, orbital energy from these objects, they will not fall to the center. Right? I should mention that. Just as we don't fall into the sun.
Archana Dwivedi has another follow-up question. What would be the end of a black hole?
Now, before the work of Hawking, it was just felt that a black hole would keep swallowing matter and keep getting bigger and bigger, and in some sense, there'll be no end. Right? However, Hawking came up with this remarkable idea that, and it's definitely too technical for me to elaborate on here. If you include what is called quantum mechanics, so which was always thought to be a theory applicable only to atoms, that the electron doesn't have a definite position, it's kind of uncertain. But the same ideas of uncertainty applied to black holes predicted that they would actually emit some radiation. Now, this seems to contradict what I told you earlier, but you can reconcile it. You can say just outside the black hole, a pair of particles forms, one of them comes out, the other falls in. Okay. So this Hawking radiation could be the end of the black hole. I mean, it's a theoretical concept because the time taken for a large black hole to evaporate like this is very, very long. But it's a major topic for theorists to investigate. Okay. So the answer is theoretically a black hole can end its life, provided it doesn't. The opposite process is where its mass increases. Okay.
So the next question is from Ian Seda, if I am reading the name correctly. Would like to hear opinions about Samir Mathur's fuzzball. I
Oh, this is very much related to what we just talked about. What is the quantum nature of black holes? Okay. And this is a topic of extremely active research. Okay. So one of the models is Samir Mathur's. Then there's another model called Firewall, which is by some other people. And interestingly, in our own Bangalore, there is Suvrat Raju, who works in the ICTS, International Center for Theoretical Science. And I think he has successfully criticized both these models and come up with his own model. So I'm really not qualified to comment. These involve general relativity is a difficult subject by itself, and quantum field theory is a difficult subject, and then this involves merger of these two difficult subjects. So it's a topic of contemporary research. Okay. I would be very happy if Samir Mathur's theory was proved correct, because he's a good friend of mine.
there is a question from Amrita Masi asking about how much distance in the universe can we see to know which things are out there. What's the extent of the universe, I believe.
Right. Okay. Now, when you observe the whole universe and map out, what object is located where and at what distance, okay, you may think that you are doing geography. Right? You're creating a map of the universe. But interestingly, you are also doing history. Because if an object is so far away and light takes, say, 3 billion years to reach us, then you are not seeing the object as it is now, but as it was 3 billion years ago. So that's an interesting thing, that when we observe the universe, we are going very far away, and we are also going into the past. Now, according to current ideas, the universe is some 13 billion years old. So that limits the extent to which you can see. And what is quite amazing is that thanks to very good telescopes, people are seeing almost up to this distance. They are seeing, say, I mentioned 13 billion years, right? So people are seeing objects which are less than 1 billion years old. I mean, that means, or rather, from our point of view, they are 12 billion years old. Okay? So people, of course, the object has to be very bright for your telescopes to see it, but this is happening. So the extent that you can observe is set by the finite lifetime of the universe.
Yeah. So there's another question from Rhapsody Home. I understand that light travels as electromagnetic waves, and yet how is it that light cannot escape the gravitational attraction? Isn't it traveling as a wave with no mass? I think it
Okay.
binds to our light as light.
Right. So, in fact, someone could have really caught me by saying that according to Einstein, all observers see light traveling at this speed. And that's exactly what Rhapsody Home is telling us. I hope we'll get the... but remember, this has to be an observer present at the location of the light waves. Right? So when you actually look at the details of the theory, there's no contradiction between these two statements. That for the distant observer who is not actually sitting where the light is moving, it appears as if the light is not able to get out. But if you were at that location, you would see the light traveling outwards. So let me state this in a more general way. So Einstein had this. He was very fond of thought experiments. If I sit in in an elevator, in a lift. So if you were in an elevator near the black hole and you looked at light, you would see light traveling with that same speed. Okay. But the reason, what the faraway observer would say is, light is frozen and you are falling in at that speed. So this has very much to do with the physical phenomena appearing different to different observers. And that's the connotation of the word relativity. Okay. So I hope that addresses this concern. So let me say, locally, a local observer will see light behaving exactly the way that we are taught. but that observer will not live very long.
So I also keep thinking about how, like in my childhood, I learned about this relative motion and stuff before. I mean, after I had already observed it in terms of trains going past each other and stuff. So it is quite difficult to understand when to introduce a concept in physics, right? Because many of these things that we are discussing are also quite complex, but many times we see in YouTube videos and elsewhere that people try to explain things using simple models like a piece of rubber stretched and then something falling, a marble falling or something like that. So how far do these models help in understanding, and do they impede in the understanding in any way?
Honestly, since I've not taught at that level, I would not know. But certainly, our undergraduate students who have the necessary mathematics and computer skills, I would tell them, yes, you watch the YouTube video, you enjoy it, but now get down to work, and you're studying for a physics degree, you do it. But at the school level, I think the teachers should really be telling us whether these, and of course, you cannot ban students from watching YouTube, right? That's no longer possible, right? So I think we have to live with the fact that there's all this material, and one has to convey to the students that some of this material is meant just to increase your interest, and what we study in the classroom, where you'll actually solve numerical problems and so on, is the direction in which your understanding will become greater. Now, yeah, that would be my very cautious response to your question.
So we'll go to another audience question. Our world asks, how did someone actually know about the expansion of black hole?
Actually, this theme of expansion is only inferred. We know that the mass and radius are proportional from the theory, right? And I guess to some extent from observations also, but the observations are not that accurate. In different galaxies, we can see, not see the black hole itself, but see the surrounding stars moving around and have an idea of the mass and size, and that is broadly consistent. Okay. Now, to see the expansion, you would have to wait for the black hole to swallow a lot of matter and increase its mass. And we have not observed black holes for that length of time. So expansion is actually indirect. It's an inference.
There is another question about from Amrita Masi. A class 8 student asked me, can black holes be created artificially? Class 8.
Okay.
That's wonderful.
Well, as I mentioned, you would have to take the mass of the Earth and compress it to, I think, 1.5 centimeters or something like that, some really small radius. But people did worry about this question when, in a different branch of physics, the physics of high energy particles. So people, again, in the newspapers would have read about something called Large Hadron Collider, where protons and antiprotons go round and round in circles, and they go and hit each other. Okay? And there's a lot of energy in a very small radius. So then some theorists actually worried, would we end up creating a black hole there? So the answer is no. Even at the LHC, with high energies that we are giving to each particle, and there's also another way of reassuring yourself that this is unlikely to happen. There are particles of much higher energy than we can create in the so-called cosmic rays, which are falling on the Earth. And even they have not created black holes so far. So my answer is a cautious no. And the technology to create one doesn't exist yet.
And that was a class 8 student. So this is exactly the kind of thing that we were talking about, how to keep the sense of wonder and then also balance the science of it. There is a question, does the black hole at the center of our galaxy have any influence on our planet? If yes, how would we study or infer this?
Right. So there's one important point I do want to make about black holes, that when you come very close to them, the gravity is very different from what Newton predicted. You have to use Einstein's theory and you get all these strange effects on light. But once you go far away, it behaves exactly like any object of that mass would behave. Okay. So maybe this is a broader point to make about physical theories. It's not that Einstein threw out everything in Newton's theory. Okay. And he could not do that because Newton's theory explained the motion of planets, explained lots of phenomena, explained the tides, explained the fact that the Earth is not spherical because it's rotating. So just by rubbing off Newton's equations and writing out a new set of equations, Einstein did not want to lose all the triumphs of Newton's theory. So the first part of his paper is to show how under certain conditions, Newton's theory will continue to be valid. So you don't have to, again, rework everything in Einstein's theory. Okay. So that includes if you're at very large distances from a body. So the simple answer is yes, the black hole at the center of our galaxy has a mass of some millions of times the sun. But we don't have to worry about the fact that it's a black hole. We just think of it as that much of mass, and then it's quite negligible compared to the mass of the rest of the galaxy, which is pulling us. So no worries on that score.
Yeah. So this also, I think, a similar question was asked about black holes engulfing other stars or part of galaxy.
So let me add that. And there I did mention many cases where that does happen, but it's all cases where the matter gets very close to the black hole, and Einstein's theory takes over from Newton's theory, so to speak.
Yeah. There's another question that has come in. One criteria by which we judge a scientific theory is by its explanatory coherence. Does it go broader by explaining more phenomena? Does it go deeper into layers of mechanisms? But black holes seem to defy the laws of physics as we understand them. For example, gravity and density theoretically approach infinity and space-time curves infinitely. Is this true? If it is, shouldn't we reject black holes or current laws of physics or the criteria of coherence? So this whole question of the physicality of the infinity bothers a lot of people.
Yes. I think the response I would give is that every theory comes with a certain domain of applicability. Okay. And you look for this coherence and explanatory power and also predicting new phenomena, new layers within that domain. But you reach the limits of that domain. So in particular, what this question mentioned is pertains to what happens to the matter after it crosses this event horizon. Okay. And goes inside, then the sort of unpleasant things which are mentioned in that question do happen. Infinite density and matter being torn apart and the laws of physics breaking down. And physicists have known this for a long time. Now, of course, if all those phenomena could propagate outside, then you would have to worry about them in the sense all your predictions could change. Okay? So the sort of small, simple name for all these unpleasant things is singularity. So where things break down. Okay. Now, fortunately, it appears that in the applications of Einstein's theory, this singularity is hidden from us. Whatever happens at the singularity doesn't come back and influence. So, of course, people would like to solve that problem, but you don't have to wait to solve that problem in order to apply the theory in other contexts. Now, the idea that these singularities are invisible to us is actually due to Roger Penrose, who received a recent Nobel Prize.
There is a question from Amrita Masi again. Why only hydrogen and helium gases are found in universe? This is again apparently from a class 8 student.
Okay, the simple answer is no. Maybe the student read somewhere that hydrogen and helium are formed in the Big Bang, right? And that's completely correct. However, once this matter forms into stars, all the heavier elements are formed. And otherwise, we would not be here because we are made of carbon, nitrogen, oxygen, iron in the hemoglobin of our blood, magnesium in chlorophyll. So all these elements have to be formed. But this Class 8 students seem to be asking the most interesting questions. Maybe the same student, I don't know. So what the student must, so I think one thing I would urge teachers is when students come up with some such statement, let's go to the source, right? Because students will pick up the most exciting statement from the source. But by looking at the source, you will find the background information that yes, hydrogen and helium are formed in the first 3 minutes of the Big Bang, right? But after those first 3 minutes, you have billions of years to form the other chemical elements.
Yeah. So hydrogen and helium are, however, are they the largest constituents of the universe?
Yes, indeed. I think if you go by counting the number of atoms, right? I think the ratio is some 1:10 or something like that. Right? If you go by weight, I think it's 1:4 because helium's heavier than hydrogen. Helium nucleus is heavier than hydrogen. And then, so all the elements that we are so fond of are really almost like some small impurities compared to hydrogen and helium. But here we are.
But as you say, we are all probably from stardust.
Yes, indeed. And it's even more than that. I mean, it's interesting. You have to make the chemical elements in stars, but some of the elements have to be made by going into a star twice. For example, our sun is functioning because it has carbon and nitrogen inside it. But that carbon and nitrogen came from an earlier generation of stars. So some of us may be twice born in stars, not just once.
Right. Yeah, that was very interesting to know. It could be a recurring process. There's a question, what does it mean when one says that black holes can evaporate over time? Does this happen to all black holes?
Yeah, this is related to the question we heard earlier. Is there an end to black holes? And this process of evaporation is proposed by Hawking. In principle, it applies to all black holes. Right? In practice, the evaporation is much more rapid for small black holes. And we don't really have evidence of such small black holes, but in principle, it could be there. For the astrophysical black holes, this is more than compensated by the increase in mass by whatever matter is falling into them. So evaporation is only one of the processes which acts in the direction of decreasing the mass. But I'm quite sure that for all astrophysical black holes, the net result is actually an increase in mass because of much more mundane process of matter falling in.
There is a question from Aditya Suresh. Could black hole really be a connection to the multiverse? If not, how could we be sure? The probability is always there that it could be or it may not be. But before we go to the answer, let me ask the audience to post their questions. I'm sure a lot of us have questions. Please do post. We can discuss. Yeah, Raja.
I think multiverses and connections, which are called wormholes, are all the subject of contemporary research, and I think it would be better addressed to a specialist. And in fact, you may still get a different answer depending on which specialist you talk about. So I will not rush in here. Certainly, Stephen Hawking has written about multiverses and so on. But I would say, and the other question is, even if there is such a multiverse, how does it affect us? Because I would like to bring in this fundamental idea that your physical theories should be connected to something that you can observe. Because otherwise it becomes, just like a story, right? So at the moment, there's no direct prediction of this multiverse and connections, but a lot of very smart people are working on it, and who knows what will come out.
And that's something that it seems the next question is asking, but I'm sure they're asking about how people went about discovering and getting to this image. The question from Our World, the name is, how did someone come to know about black hole and stuff like its high gravity?
Initially, completely theoretically. That is, Newton gave us this inverse square law, right, which has the mass in the numerator and the radius in the denominator. So then maybe not very much after Newton, actually. Maybe 70, 80 years after Newton, in France and also in England, people just pushed this formula to its limits. So you had a formula for escape velocity, right? Which again has mass in the numerator and radius in the denominator. So if you want to make this escape velocity higher and higher, then you have to either keep the radius fixed but keep increasing the mass, or you could, keep the mass fixed and keep decreasing the radius, which is the route that these people. But it's really a pen and paper exercise, which was done by the French scientist Laplace, by English scientist Michel. But it was really speculation because no one had tested Newton's laws in a region where the escape velocity was approaching the velocity of light. So I would say that, the question was, how did people know about? So they didn't know, they guessed. And it took many centuries for that guesswork to become knowledge. But today, it's not just knowledge. I think anyone who enters astrophysics will take black hole as a very routine thing. Yes, of course, we have a black hole in this place, in that place. This is emitting that much. This is orbiting around that. These two have merged. So in some sense, it's become part of the currency of astrophysics.
You mentioned that historical development of black hole in your article as well as now. Is that a good way for a school student to get motivated to read about something, the history behind a concept or research work? Is that a good way to introduce someone to research?
Yes, but perhaps not too early. I do not know. I think what I understand of education, I've not directly participated in school education, but sitting in APU, you're exposed to a lot of it. I think in the early standards, exposure to direct experience, like the Montessori method and so on, seems to be the most effective. And in fact, one worries that there's a lot of premature exposure to second-hand experience, virtual experience, which is happening right now. But that's a question for the education specialists or even the parents should worry about that. Like, in the Montessori method, the child will learn to pour water from one glass to another, maybe thread a needle, develop this hand-eye coordination and so on. And should one lose that just by a premature exposure to a lot of virtual material? But definitely, at some point, students will start asking bigger questions. And we know that some students start asking this even at 8th standard, right? At that point, you can say, okay, look at the history. But everything is a matter of balancing time, this poor student probably by 9th or 10th standard will be going to a tuition class, maybe missing the games period. I don't know. So these are very difficult questions, and I won't claim to be an expert on that.
A lot of us wonder about the balance in education, of course. There is another question. Now that a black hole has been imaged, what questions about black holes remain?
Okay, so this image, I think, was published, if I remember right, in 2018, but the people didn't keep quiet. One of the predictions of the model is that the ring of matter comes, but then you can ask, what is this friction which makes it fall? So one of the models was that it's due to magnetic fields. Now, how can you detect whether there's a magnetic field or not? It turns out that radio waves are a good tool to do that. If the magnetic field has a certain direction, then the radio waves will have a certain property. Right? So in the next round of observations, they looked for this property and they believe they have found it and they've published it recently. Then they would not stop. They want to now look for other black holes, like the one. It's a bit of a surprise that they look at M87, which is so far away, and only then they will try to look at our own black hole. But the reason is very simple. Our own is a mini black hole compared to M87. Instead of billion, you have million. So actually, it's easier to observe M87, much harder to observe our own. And yes, I think they will continue. And if the whole Earth is not enough, they will launch a satellite. So this will not stop.
Yeah, quite fascinating. The topic of black holes and how to introduce those topics to school students. Do you have any concluding thoughts from the article, the discussion?
No, I would, you know, I would again be a little cautious here. We are addressing an audience of teachers who are really at the front line. They are facing these students with all their curiosity, all their variety, all their constraints. And although I have got a little exposure to this in Azim Print University, perhaps less so when I was working in various research institutes, I think I would offer whatever I can to the teachers. And they are the best people to make use of whatever is useful to them. I hope something was useful. And let's also remember that the teachers are people qualified in the various subjects. They might want to keep their own knowledge of the subject alive, right? So I would say that is what I would contribute, if at all.
There is one last question also. Uh, uh, and if you permit, we can take that. Rajaram, what do you?
No, sure,
So
sure.
the question is, what could be the material present inside the black hole?
Oh, again, a marvelous question. So we can't directly observe it. What we do know is what the material was before it fell into the black hole. If it was a gas in a galaxy, as someone mentioned, it may be mainly hydrogen or helium or something like that. But one of the interesting things is, interesting properties of black holes, is that the external property doesn't seem to depend on the material. And for the reason that we just discussed, that all those properties of the material which have gone inside, that influence is not able to come outside. So this was put in a very interesting way by a scientist called John Wheeler. He said you can make a black hole out of protons, or you can make it out of television sets. It doesn't matter. It will ultimately behave the same way as far as the outside world is concerned. So he said black holes have no hair. He's bald. He's just a sphere as far as you're concerned.
That is a very nice way to put it. So Rajaram, and to all those who joined, we thank you. May not have been able to take a lot of questions that people might have. We've tried our best from the queries that have come in the comments and before. Join us again for our next webinar on August 11th, 2021. And for all those who've not yet subscribed to iwonder, please do so. Thank you.
If there are extra questions and they can be conveyed to me, I'm happy to respond over email.